Our work is on compositional embeddings for multi-label one-shot learning. First, what is one-shot learning? Basically, we want the model to classify objects that are not seen during training, and we will give the model a single example of each class. Here's an example of five-way one-shot learning. Five-way here means we will give the model 5 reference images. And a typical way to do one-shot learning is to train an embedding model at first. Then we use the embedding model to extract embeddings from the test image and the reference images. Then we compare the embedding distance between the test image and reference images and choose the smallest one. With traditional embedding models, a single embedding only represents feature of one object. In contrast, we propose a compositional embedding model that can represent multiple objects per embedding. Here's a schematic shows how our compositional embedding works. We propose two functions, composition function G and query function H. G will compute the compositional embedding of a data sample which contains multiple singletons, and query function H will answer whether a singleton is contained in a composite sample. During training, we will let the loss backpropagate through the embedding model and the composition model at the same time, so they are optimized at the same time. Our experiment 1 is conducted on OmniGlot. First, we try our F and G on OmniGlot. We try to answer which subset of the reference classes are contained in the test image. And one way to use traditional embedding model to deal with this problem is to compute the mean of embeddings from singletons and use the result as the compositional embedding. We compared our F and G results with the traditional embedding baseline, and we can see that our result actually outperforms the baseline by a large margin. We also tried different architecture for the G function. The results show that if G has only one layer, then it has the best results. Then we try our F and H on OmniGlot. We use the same rendering method used in experiment 1. And here, the model tries to answer whether XB is contained in XA. XA is associated with 1 to 5 classes. Half of XB are positive and half are negative. The results also show that F and H outperform traditional embedding baseline, and unlike the previous experiment, H function actually works better when it has 3 layers. Experiment 3, we try our F and H function on open images. Here's an example of open image on the right. So XA is a test image, and XB could be a dog, a trousers, a shoe, a countertop, and a caterpillar. And for XB, ABC are contained in XA, DE are not contained. The results also show that F and H outperform 2 baselines, and when H function has 3 layers, it works best. For the 2 baselines here, they can be found in our paper. We developed a compositional embedding mechanism that can capture set relationships, and it strongly outperformed baselines based on traditional embedding. Compositional embedding potentially allows not only singletons, but also information from multiple objects and their structure being packed into the same embedding space. And it can be used in different tasks, like it can be used to recognize individual speakers in overlapping speech. It can be used for multi-label recognition, and it can even be used to decompose an object into individual parts and individual properties recursively.